It is really, really, really important that you learn to be good at reading graphs, partly because as you continue in science class in the spring and in your biology and chemistry and physics classes, you will really need to be effective at this, partly because there are lots and lots of graphs on ACT Aspire and ACT, PSAT, all of those tests. And also just because to be an informed human being, it's good to be able to look at graphs that people show you and understand what they mean so that you won't be fooled by misinformation and so that you can use data to make decisions for yourself. So we are going to use information from the Balloon Jet Lab that we did a 3 weeks ago in order to review the parts of a line graph and review some information about reading them and interpreting data from them. So I've drawn out a graph here. I've drawn the x-axis and the y-axis. The x-axis is always used to show the independent variable. We can also call this the manipulated variable because it's the variable that we as researchers, as scientists, as the people in charge of what's going on can change. It's interesting to note that when time is displayed on a graph, it is almost always shown on the x-axis. And you might think, well, that doesn't make sense because we can't manipulate time. Time shouldn't be an independent variable. And, we can't manipulate time. But what we can decide is at what intervals we're timing something. We can decide when to look at the activity that's going on. So in that way, it is an independent variable. In this example of the Balloon Jet Lab, I've put seconds on the x-axis. So after 1 second, after 2 seconds, 3, 4, and 5 seconds, we observed the activity of our balloon jet. And then on the y-axis is the dependent variable. It's also called the responding variable because that's the variable that responds to what's going on here. In other words, at 1 second, is our balloon at 10 meters, 20 meters, 30 meters? Where is it? That depends on the location of the balloon, depends on what time has gone by. So the dependent variable or the responding variable is always shown on the y-axis. And if we're making a graph, we want to be sure that we label it properly. We want to be sure that we show the people that are going to be reading the graph what to look for. A graph that isn't clearly labeled is sort of useless. It's hard to understand what's going on if we haven't communicated well. So in this case, again, the Balloon Jet Lab, you may remember that the Balloon Jet Lab was done partly to demonstrate Newton's third law of motion, which we'll discuss in a video here in maybe 3 videos from now. Newton's third law of motion says that for every action, there's a reaction. In other words, forces come in pairs. So if air is blown out the back of a rocket or a jet or, say, a balloon, the balloon is forced forward. Forces come in pairs. The other reason we did this lab was to show that force and mass are related to acceleration. So we took just a plain balloon, filled it with air, put it on a string, let it go. And let's say that on average, your balloons that did not have anything taped to them went from 0 to about 30 meters in about 5 seconds. So let's label this balloon without additional mass. So it went the farthest. Then how would we draw it if in 5 seconds the balloon with one nail only went about 25 meters? Well, we'd go, okay, we timed it at 5 seconds. Here's 25 meters. We'd put it about here, right? And since we didn't really time anything in the intervening time, we'll just draw it straight. So let's label this balloon with one nail. So how would we indicate the motion of a balloon with two nails? Well, find another color. Here we go. What if the balloon with two nails only managed to go 10 meters in that 5 seconds? We draw that line like this. Balloon with two nails. So what if we were asked questions about interpreting this as it relates to Newton's third law? Which balloon went the farthest? What's the one with the least mass, right? Which balloon went the slowest? What's the balloon with the most mass, right? 10 meters in 5 seconds. If we figured out its speed of two-nail balloon, if it went 10 meters in 5 seconds, then we could simplify that to be 2 meters per second, right? Put that up here, 2 meters per second. Could we figure out how fast the balloon with one nail went? Sure. Let's put it up. Yeah, we'll go here. One nail balloon. It went, what did we say, 25 meters in 5 seconds? Let's simplify that to be 5 meters per second. The balloon without any additional mass went 30 meters in 5 seconds. We can do that. 30 meters in 5 seconds simplifies to 6 meters per second. So these aren't exact, but they do serve to indicate that the more mass something has, the slower it goes, the less it accelerates. Now, what if we were asked on by a test question something like, what was the location of the balloon with one nail at 2 seconds? Would we be able to figure that out? Well, hopefully we would. We could go over here to 2 seconds. We're looking for the green line because that's the balloon with one nail. We could go up here. Oh, it looks like that nail was somewhere around the 10-meter mark at that time. What if we were asked, what is the location of the two-nail balloon at 4 seconds? We could do this, right? Find 4 seconds, go up here, go across. Looks like about 8 meters. So we could answer that question by saying the balloon with two nails was at about 8 meters at 4 seconds if it was traveling at constant velocity. So hopefully you could use a graph like this to interpret data and answer questions on my test or on an ACT type test, or if you just saw information like this in the newspaper or a magazine or online or on the news, you'd be able to use it to get information and interpret it for yourself.